Hello chemists and welcome to today's video. We're going to be looking at nucleophilic addition applied to the reduction of ketones and aldehydes. We're then going to look at the formation of hydroxy nitriles, also from ketones and aldehydes. We're then going to explore a concept called chirality and how chirality can result in optical isomerism, which is a type of stereoisomerism which you may have come across before when looking at alkenes and EZ geometric stereoisomerism. This is quite a technical video, so I would recommend that you pause, replay parts of the video if you haven't fully understood. And remember, there's always great videos available online from other vendors as well, which you could use to enhance your understanding. I hope you enjoy the video. Let's get started. Okay, so in this first video, we're going to look at how an aldehyde can be converted into an alcohol. Typically, we'd be looking at converting alcohols into aldehydes the other way round via oxidation. But in this example, we're actually going to look at reduction. So that's converting an aldehyde back into a primary alcohol. I've drawn a reaction scheme here for you, and you can see that we've got our aldehyde here, and this H in square brackets represents our reducing agent. So you might remember that an oxidizing agent is shown as O in square brackets. Reducing agents are shown as H in square brackets. And that's typically because of the fact that oxidizing agents are historically known as the addition of oxygen, whereas reduction historically is the removal of oxygen or the addition of hydrogen. So H in square brackets is a reducing agent, O in square brackets is an oxidizing agent. So you can see we've gone from ethanol here and we've resulted in the product of ethanol. Okay, and we've added two hydrogen atoms, one on the oxygen here and one on the carbon here. You can see, so that's why we needed two reducing agents effectively in the balanced equation. So the mechanism for this one is nucleophilic addition, and the reagents and conditions are as follows. You need to use a reducing agent, as I've described earlier, and the reducing agent you're going to use for this one is sodium borohydride. That has the formula NaBH4. This needs to be done in water and with methanol. So here's my aldehyde, and you'll notice here I've drawn H-. That thing's name is hydride, and it's a negatively charged hydrogen ion, and that is going to act as our nucleophile in this reaction. We've got a carbonyl here, functional group C double bond O, that forms the aldehyde, and this carbon will be delta positive and the oxygen will be delta negative because oxygen is the more electronegative of the pair. So we've got a polar bond there, polar carbonyl group. So our nucleophile is going to attack the delta positive carbon, and this is going to break one of the bonds in the CO double bond. So we show that as follows, a pair of electrons moving onto the oxygen. Now that will create an intermediate, and this is called an alkoxide intermediate because you've got a negatively charged oxygen atom bonded to a carbon. So an alkoxide intermediate. Now if you look at the difference between this intermediate and the product, well, the only real difference is that there's a hydrogen here on this oxygen that we need to put on here. Now if this is negatively charged, we need to neutralise that negative charge with a positive charge. So what we've got to add to this is a bit of H+. Now that either comes from the water or the methanol that's been added to this reaction mixture. So the alkoxide oxygen atom is going to attack the H+ ion there, and then it will be protonated, as we say, and then you'll end up with your alcohol, in this case ethanol. Next we're going to look at how a ketone can be reduced into an alcohol. You should remember that ketones are the product of oxidation of secondary alcohols. Therefore, if we reduce a ketone back into an alcohol, we should get a secondary alcohol. I've drawn a reaction scheme here. You can see that we've got propanone, and we're going to react that with 2 moles of our reducing agent, and that will achieve the product here, propan-2-ol. Let's have a look at the mechanism for how this works. It's nucleophilic addition, and again we're going to use that same reducing agent, sodium borohydride or NaBH4. This will be in water with methanol. The mechanism for this one is exactly the same as you've previously seen. A hydride ion, a polar carbonyl group. The hydride ion acts as a nucleophile, attacking the delta positive carbon. We break the carbonyl bond to form an alkoxide intermediate. H+ from the solvent protonates the alkoxide intermediate, and there we have our product. So you can see this mechanism is the same, it's just as if I've shifted it along one in the chain that you saw earlier. Now let's look at how we can convert aldehydes into hydroxy nitriles. Here I've got an aldehyde and I'm going to react it with potassium cyanide. I also need acid to ensure that we're able to protonate the alkoxide intermediate. You can see that we've gone from an aldehyde to this structure here, which is called a hydroxynitrile. That's because it contains both the nitrile functional group and the hydroxyl functional group. Let's have a look at the name of this compound now. This compound's name is 2-hydroxypropane nitrile. Naming hydroxynitriles can be a little bit challenging. The first thing you need to know is that the longest chain includes the nitrile functional group. So here we can see, starting at the nitrile functional group, we've got 1, 2, 3 carbons. Carbon number 1 will be the carbon of the nitrile. So this is propane nitrile, where the nitrile is position 1. Therefore, the hydroxy functional group is on carbon number 2. So this becomes 2-hydroxy, there it is, propane nitrile. No need to number the nitrile because it's considered as carbon number 1 in this example. The mechanism is again nucleophilic addition, and the reagents and conditions are a little bit different for producing hydroxynitriles. We're going to use potassium cyanide, which has the formula KCN, and then we're going to follow that up by adding dilute acid. We can show that here on the reaction equation as H+. Alternatively, instead of adding KCN followed by dilute acid, you could just bubble through gaseous hydrogen cyanide, which has both the H+ and the Cn- you need for the reaction. The mechanism works as follows. We have the cyanide nucleophile here, Cn- with a lone pair of electrons shown here. Again, we have a polar carbonyl bond, delta positive on carbon, delta negative on oxygen. Our nucleophile will attack the delta positive carbon. This will break one of the bonds in our carbonyl to form an alkoxide intermediate. Here it is. I've shown the nitrile beneath, but you could show it on either side. Now we need to protonate the alkoxide intermediate via the addition of H+. The lone pair on oxygen will attack the hydrogen ion, and then we'll have our product. Next, let's look at how we can convert a ketone into a hydroxynitrile. I've drawn a reaction scheme here. Now we've got a ketone, this is propanone, and this is more commonly known as acetone, now varnish remover. Again, we're reacting it with potassium cyanide and acid. You can see we've made our hydroxynitrile product here. Let's consider how we would name this. The longest chain must include the nitrile group. I've shown it here. Let's count for a long chain. 1, 2, 3. So we're looking at a propane nitrile here. The changes to functionality occur on carbon number 2, where we have both a hydroxy functional group and a methyl group. We need to consider which of these we would put first in the name. H for hydroxy comes before M for methyl in the alphabet. So therefore, we're looking at 2-hydroxy, 2-methyl propane nitrile. I've shown here K+ as a byproduct, but in reality this is going to pair up with whichever counterion your acid has to H+. So if we used hydrochloric acid, this would be potassium chloride as a byproduct. Our mechanism for this reaction is again nucleophilic addition. And the reagents and conditions are again potassium cyanide, KCN, followed by dilute acid or the use of gaseous hydrogen cyanide. Our mechanism is much the same. We're going to start by labelling our partial charges on our carbonyl functional group, with carbon being delta positive and oxygen being delta negative. Our cyanide nucleophile will attack the delta positive carbon, and the carbonyl bond will break to form an alkoxide intermediate. H+ from the acid will then be used to protonate the alkoxide intermediate to form the hydroxy functional group. And there we have our product. Nucleophilic addition reactions are of particular interest in A-level chemistry because they introduce you to the concept of optical isomerism, which is a form of stereoisomerism. You should have seen stereoisomerism before and know its definition. Compounds with the same structural formula but a different arrangement in space. The type of stereoisomerism you'll likely have seen before is EZ or geometric stereoisomerism. This is the type that's associated with alkenes. We can see here both of these alkenes are buteene, but one is named E-buteene and the other Z-buteene. The E stands for entgegen, meaning opposite. We can see that on the left-hand side of the CC double bond, the group with the highest priority is this methyl group, And on the right hand side of the CC double bond, the group with the highest priority is also this methyl group. But because they are on opposite sides to one another, we get the E nomenclature. In Z-butene, the highest priority methyl group on the left hand side of the CC double bond is on the bottom, and the highest priority group is also on the bottom on the right hand side of the CC double bond. So because the two highest priority groups are on the same side, then we get the Z nomenclature, meaning together. This is the type of stereoisomerism that's specific to alkenes. And it only occurs when both the left-hand side and the right-hand side of a CC double bond have two different groups. Both have to have two different groups. That's not to say that the two different groups have to be different to each other comparing each side. It's just that on one side you need two different substituents or groups. And this is the result of restricted rotation around the CC double bond, meaning that I wouldn't be able to switch this CH3 group and put it down here because this bond here can never rotate. The type of isomerism we're looking at related to nucleophilic addition is called optical isomerism, again a type of stereoisomerism. Here I've shown you an example of optical isomerism, and you'll notice that it includes carbon atoms. Both of these molecules look exactly the same, but there are optical isomers because they are non-superimposable mirror images of each other. They both have the same structural formula, but their arrangement in space is different. This is the result of a chiral atom. In this video we're only going to be exploring optical isomerism in carbon, so I'm going to link all my explanations to that. A chiral carbon atom is one with 4 different groups. You can see that this carbon has a hydroxyl, a hydrogen, a methyl and a bromo group. Because the carbon atom has 4 different groups, there are different ways to arrange these 4 different groups around the carbon atom. And no matter which way we rotate the molecule, we won't be able to superimpose, that means to lay over one another, these 2 different optical isomers. We can call these optical isomers non-superimposable mirror images or enantiomers, and a key feature of optical isomers is that they rotate plane polarised light in opposite directions. Let's explore optical isomers more. First, I'd like to clarify some terms. I'll be using the word chiral to describe a carbon which has 4 different groups, like the example I just showed you. I'll be using the word achiral to describe a carbon which doesn't have 4 different groups. In other words, at least 2 or more of the groups around the central carbon atom will be the same. Take this example here, it's achiral because it has 2 of the same group, this hydrogen atom here. It's important to remember as well that the way that I'm showing these molecules is a 3D representation. We can imagine it like the ball and stick model here. We can use wedges and hashes to show bonds coming both out of the page or going back into the page. See how this bond is coming out towards us? We would use a wedge to show that, like this methyl group here. And you can now see how this bond back here is going back into the page, there it is, and we would use a hash to show that going back into the page. Now let's try to create some optical isomers. I've drawn a molecule here with a chiral centre. You can see it has 4 different substituents. The carbon has a hydroxy group, a hydrogen group, a methyl group, and a bromo group. Optical isomerism is the result of these 4 different groups being arranged differently around this central chiral atom. So let's swap the bromo group for the methyl group, so the bromo group is coming out of the page and the methyl group is going back into the page. This is an example of an optical isomer of this original structure. Optical isomerism, remember, is a type of stereoisomerism, so these 2 do have the same structural formulae, but their arrangement in space is different. However, this isn't the ordinary way in which we would draw an optical isomer of this structure here. What we need to do to prove that this one is an optical isomer is show that there is no way we can rotate this structure so it will become the same as this structure you see originally on the left. So what I'm going to do is try and rotate this structure in a bunch of different ways and see if it becomes the same. So let's rotate it where we're looking at the y-axis going through the centre of the molecule, bringing it round, spinning it around. So let's move this methyl group to here, the bromo group to here, and the hydrogen group round here. We'll leave the hydroxy group in place though. You can see after that 120-degree axial rotation that the 2 compounds are still not the same. There's no way I could overlay these 2 structures so all of the atoms land in the same places. Let's try and rotate it 120 degrees again. Well, it's looking more similar because the bromo groups are in the same place, but you can see that the hydrogen and the methyl groups are switched around, so it's still not the same. Now in this example, I've only rotated axially, in other words, to spin it around on its axis. You could obviously try rotating it around horizontally or equatorially as well. If we try to overlay the two structures, we can see that they're not the same. So therefore, we can say that these two structures are non-superimposable. And now if I perform a slightly different rotation, where I basically flip this molecule around, then what we actually find out is that this structure that we've been working with is a mirror image of our original structure. So that original swapping of these two groups resulted in our new structure being a mirror image. And no matter how we try to overlay this structure upon this structure, they are non-superimposable. When we pair up the words non-superimposable with the term mirror image, we are describing optical isomers, which are often also described as enantiomers. This is because we have created an optical isomer which is a non-superimposable mirror image. These two are non-superimposable mirror images of each other, and that is the result of the different arrangement of the 4 different substituents around the chiral carbon atom. And remember that these are stereoisomers of each other because they have the same structural formula but have a different arrangement in 3D space. Chemists need a way to distinguish between optical isomers, and this is typically due to pharmaceutical drugs. Only one of the optical isomers is typically active on the active site of an enzyme within your body. So therefore chemists need to make sure that when they create drugs, they're only giving you one of the optical isomers. The other optical isomer, or the other enantiomer as we could call it, may have negative effects or harmful effects. So we need a way to check that we've got the correct optical isomer. Chemists use a property of the optical isomers that enables us to tell the difference between the two. If we were to shine plain polarised light at 2 different samples, let's say we've got this optical isomer in one test tube and this optical isomer of the original in another test tube. We'll shine plain polarised light through both samples. One of the optical isomers will rotate the plain polarised light in a clockwise or positive direction. The other optical isomer will rotate the plain polarised light in an anti-clockwise direction. So therefore, if you know this sample well, if you shine plain polarised light through an unknown sample and it rotates it clockwise, then you know you're looking at one particular optical isomer. If it rotates it anti-clockwise, you know you're looking at the other optical isomer. However, it could be that you're looking at something called a racemic mixture. And this is when the pair of optical isomers exist in an equal ratio, often described as a 50-50 ratio. What we're talking about here is a test tube that doesn't contain one optical isomer or the other optical isomer. We're talking about a test tube that contains both optical isomers at once in an equal ratio. And racemic mixtures are typically produced by nucleophilic addition reactions. And this is because in nucleophilic addition reactions, a chiral centre can often be made during the reaction. Now, racemic mixtures are not optically active at all, which means that they have no effect on plane polarised light. Let's explore why that's true. If we shine the plane polarised light through a test tube that contains both samples at once, then one of those enantiomers will rotate the plane polarised light in a clockwise direction. You can see how I've shown this here. This side looks like it's gone down and this side looks like it's gone up from the original plane polarised light, so therefore it's been rotated clockwise. The other enantiomer will rotate the plane polarised light in an anti-clockwise direction. See how I've shown this side going down and this side going up, so we must be rotating in an anti-clockwise direction. Now if that's happening at the same time, then the effects are going to cancel out, so you're not going to get any effect on the plane polarised light. This is a really important point though. The exam board wants you to write this in a very specific way. With a racemic mixture, it has no effect on plane polarised light because we can say the pair of optical isomers exist in an equal ratio and each optical isomer rotates the plane polarised light by equal amounts but in opposite directions, and this cancels out the rotational effect. This wording that I've shown at the bottom here is essential to get marks. you need to say by equal amounts but in opposite directions. Don't just say in equal and opposite directions, which is a common mistake. Now let's examine why nucleophilic addition can result in a racemic mixture of optical isomers. In every nucleophilic addition that I've shown you today, we show a nucleophile attacking a carbonyl group. This forms an intermediate where the carbon has 4 bonds. You can see in this intermediate here, this carbon intermediate has 4 different substituents. Therefore, the product of this nucleophilic addition will be chiral. And therefore, if it's chiral, it has the opportunity to exhibit optical isomerism. The reason for the racemic mixture is all about this carbonyl group here. And it's important that you know that a carbonyl group has a trigonal planar structure. I've shown it rotated and in 3D here. You can imagine this as a flat plane where this atom here, this atom here, this atom here, and this atom here all exist on a flat plane. That's what the planar mean in trigonal planar. Planar meaning flat, trigonal meaning to form that triangular shape when you join up all the corners. Remember that the bond angles here also are 120 degrees. This trigonal planar carbonyl group is the reason for the racemic mixture caused by nucleophilic addition. Let's explore how the planar carbonyl group results in a racemic mixture. If we imagine the planar carbonyl group as a 3D diagram, as I've shown here, we know it's going to be attacked by our nucleophile. But because it's flat or planar, there's only really 2 ways that our nucleophile could attack. It could attack from above. If it does so, then it would have the effect of forcing these 3 groups down. That would result in an intermediate alkoxide, which looks a little bit like this. Let's now consider the alternative topicity, that means direction or face, of attack. Where else do you think that nucleophile could attack? Hopefully you've decided it could also attack from below the planar carbonyl group. If it did this, then it would force these 3 other groups up, resulting in this alkoxide intermediate. Now let's consider those 2 intermediates that we formed as a result of the nucleophile attacking from both above and below the planar carbonyl group. Here we've shown our first intermediate as the result of the nucleophile attacking from above. Here we've shown our second intermediate as a result of the nucleophile attacking from above. Notice how both intermediates are chiral and the addition of H+ would protonate them to form the final product. Now what we can try to do is rotate this structure here to see if we are able to superimpose it upon the original structure. If I rotate it by 180 degrees, in other words, bring this nucleophile group to the top here, X and Y, and the alkoxide down to the bottom. After rotation, I can see that the X and Y groups have been switched around. We have a different arrangement of the 4 different groups around the central chiral carbon atom. Now if I rotate it 180 degrees in this direction, we can now see that we've created non-superimposable mirror images. So by rotating both structures and comparing them, we've found non-superimposable mirror images, so therefore we're looking at optical isomers or enantiomers. And because there is an equal chance of that nucleophile attacking from above and below the planar carbonyl group, these optical isomers will exist in a 50-50 equal ratio. So therefore the mixture that's produced as a result of the nucleophilic addition will be racemic, and it will have no effect on plain polarised light. Now let's perfect our wording of this phenomenon for an exam purpose. The first thing you need to state is that the carbonyl that is involved in the nucleophilic addition reaction is trigonal planar in terms of its shape. The second thing we need to state is that the nucleophile has an equal chance of attacking from below or above the plane. The third statement we need to make is that this results in a racemic mixture, which is an equal ratio of the enantiomers. And the enantiomers are non-superimposable mirror images of each other. Now let's apply these concepts of optical isomerism to some of the examples of nucleophilic addition that we saw earlier. The first example of nucleophilic addition we looked at was the reduction of an aldehyde. Reduction of aldehydes always results in the formation of a primary alcohol. The only part of the molecule that's changed is this end carbon here. So this is the carbon that we need to look at when we're considering as whether optical isomers could be produced. If I look at this carbon atom here, which has been changed, I can see that it's achiral because it doesn't have 4 different groups. 2 of the groups are hydrogen, so it's not chiral. We use the word achiral to mean not chiral. I've shown it here as a 3D representation, and you will commonly be asked to do this. Basically, all you do is you take the carbon atom that's changed and you draw the groups around it in 3D. But any longer chains, you write those as structural formulae. You can see I've written it in the form of CH2, CH3, reading from right to left here. So we can see that the reduction of an aldehyde does not result in enantiomers or optical isomers, because the carbon that's changed isn't chiral. Now let's have a look at the reduction of a symmetrical ketone. What I mean by that is that the carbonyl functional group is right in the middle of the molecule, and you could draw a plane of symmetry and replicate the structure. Again, we're going to reduce it, and reduction of ketones always results in secondary alcohols. Again, if we look at the carbon that's changed, which was this one here, we can see that this is still not chiral. We've got a hydroxy functional group, a hydrogen, and then we've got 2 methyls. So because those methyl groups are exactly the same, this is achiral. Again, I've drawn a 3D representation here. As it's achiral, you won't get optical isomers. Now let's have a look at reduction of an asymmetrical ketone. You can see here I can't draw a line of symmetry and result in the same structure because the ketone is not in a central position in the chain. This reduces again into a secondary alcohol, but now let's examine about the groups around that central carbon atom. We've got a hydroxy group, a hydrogen atom, a methyl group, and an ethyl group. Some of you might be thinking, well, actually this has got 2 carbons bonded to it. It's not about the atom directly bonded to the atom you're looking at, it's about the whole group directly bonded. So we count this as a methyl and this as an ethyl. A 3D representation as well can show that this is a chiral carbon. We often note a chiral carbon using an asterisk. We could draw a mirror image of this structure to represent its optical isomer. All you need to do is draw a mirror image of it, but get the letters the right way round. So you can see the CH3 groups are both facing each other, the OH is still on top if mirrored, and this ethyl group has swapped sides, and the hydrogen groups on the bottom. So this here, the reduction of an asymmetrical ketone, does result in optical isomers. Now let's have a look at the formation of some hydroxy nitriles via nucleophilic addition. We'll start with an aldehyde. Here I've got propanal and I'm reacting it with potassium cyanide and hydrochloric acid. I form this compound here. In terms of the naming, we count the nitrile carbon as carbon number 1. We count a chain of 4 from that carbon, so we're looking at butane nitrile. And the hydroxy group is on position 2. So this will be 2-hydroxy butane nitrile. If we examine the carbon that's changed, which was this carbon here, which is here, we can see that it's got a hydroxy group, a nitrile group, a hydrogen group, and an ethyl group. So therefore, it does have 4 different substituents, so it's chiral, and we can mark it with a star to show that it's chiral. I'll draw a 3D representation of it here as well, and then I'll show its optical isomer. So that chirality resulted in optical isomers. Next, let's have a look at the formation of a hydroxynitrile from a ketone which shows symmetry. Here I've shown propanone or acetone, same reaction conditions. The nitrile group's going to go here, and this will become an OH group. There we are. Let's try and name it. So our longest chain, counting from the nitrile group, 1, 2, 3. So we're looking at propane nitrile. And then on position 2, we've got methyl and hydroxy. H comes before M in the alphabet. So this is 2-hydroxy, 2-methyl, propane nitrile. Let's examine the carbon atom that's changed, the one in the centre. We can see that it's got a nitrile group, a hydroxy group, and then 2 methyls. Because 2 of those groups are the same, this is achiral. Even in a 3D representation, there's no way I could draw an optical isomer of that which is non-superimposable. Therefore, this symmetrical ketone does not result in optical isomerism. Now let's have a look at the formation of a hydroxynitrile from an asymmetrical ketone. Here I've shown butane 2-one, same reaction conditions, and there's my product. Let's try and name it. Carbon number 1, 2, 3, 4 in the longest chain. So we're looking at butane nitrile. And then on position 2, I have a methyl group, and position 2, I have a hydroxy group, H before M, 2 hydroxy, 2 methyl, butane nitrile. This carbon here is chiral because it has 4 different substituents: a hydroxy group, nitrile group, methyl group, ethyl group. We'll mark it with a star to show that it's chiral, and then we'll draw its optical isomer pair. Remember, the optical isomer pairs are known as enantiomers of each other. Let's finish off by thinking about what requirement a nucleophilic addition must have in order for you to form a racemic mixture of enantiomers. The only examples that formed a racemic mixture of enantiomers, or a pair of optical isomers in a 50-50 ratio, were those where the starting material exhibited asymmetry. In other words, you couldn't draw a line of symmetry down through the functional group that's being attacked. So asymmetry in the starting material results in a chiral centre being formed, and therefore you get a racemic mixture of enantiomers. Well, that was pretty full on, wasn't it? Okay, so do rewatch bits of it if you need to, but otherwise I hope you found that video helpful, and I'll see you in the next one. Goodbye.